Okay, so let's look at question 5. Here we're given that we need to consider a container of volume divided into two compartments of equal size. So in other words, the total volume of the container is 5 cubic decimeter. And then there's nitrogen at 1 atmosphere and 25 degrees Celsius in the right compartment. There is hydrogen at the same temperature and pressure. It's an important point. And then calculate the entropy and Gibbs energy of mixing when the partition is removed. Assume the gases are perfect. Right, so in other words, what is the situation that we are given here? Well, we have a box that has a compartment. So on the left hand side, let's say, so we have nitrogen gas here on the left hand side, and then on the right hand side we have hydrogen gas. And both are at 1 atmosphere and 25 degrees Celsius, right? So in other words, there's no distinction there. And then the partition is removed. So in other words, they're allowed to mix. So then they mix. And they're both perfect. So it's a simple application of the mixing of perfect gases at the same temperature and pressure. So it's something that we've already encountered before. So what we can use is our equation for the mixing of, or the Gibbs energy of mixing. So in other words, we need to look at this equation, which says that the Gibbs energy of mixing is equal to nRT, and then it's equal to something equal to the mole fractions of the different gases. So I mean, I'm just using general what's the word I'm looking for, like general subscripts here at the moment, A and B for the gases, but you know, A is, for example, nitrogen, so we can make it N2, and then B is hydrogen. Okay, and then because they're perfect, nRT can be equal to PV, because we're given pressure and volume. So we don't have the number of mole of the gases, we have pressure, and we're given volume of the container, because we're given its consider the volume of a container is 5 cubic decimeter. So that's something we're given, so we would rather use that. Okay, so basically all that's left here is then to well, we can rewrite this a little bit easier, because it's two perfect gases of equal temperature, pressure, and equal volume at the beginning. So PV, it means their mole fractions are the same. So in other words, the mole fraction is a half, and then we have ln a half. Right, you agree? So I'll quickly explain. Let me just write this, then I'll elaborate on that. So we have half of the perfect gas. So if we just ignore the fact, we just look at this as a, you know, a perfect gas, you know, unidentified nitrogen and hydrogen gas, and there's the same number of gas molecules. There's 4 of them on the left hand side, there's 4 of them on the right hand side. Then what's the mole fraction of them on the left hand side? It's 4/8, and on the right hand side it's 4/8. So in other words, there's no more on the left hand side than there are on the right hand side, so it's a half and a half. It's what it, so you can just plug in all of them. So then this becomes if you just quickly, so you can do your Lin rules. You can plus this together, then this becomes ln of 2, because ln of, so you have a half ln a half plus a half ln a half becomes ln a half, and then that becomes ln of 2. So we have that. So then we just have to plug in our pressure value. So our pressure is given as 1 atmosphere. 1 atmosphere in pascals is 1 atmosphere to Pascal atmosphere. There is a 1., there's 100, 325 Pascal in an atmosphere, and then our volume is 5.0 cubic decimeter. And how many decimeters is there in a cubic meter? There is 10 cubic decimeter in a meter. So we have meter and we have decimeter. There's 10 cubic there. There's 10 decimeter in a meter. Then we have meter cube, so we can plug that in. And then we of course have ln of 2. This thing gives us a value of minus 3.5107 and so on times 10 to the power 2 joule, which then you can round off to minus 0.35, so 2 significant figures because of the 5.0 decimeters kilojoule, so minus 0.35 kilojoule. Okay. Then for the entropy of mixing, so delta mix S, that is equal to simply, you can use one or two things. I mean, you can either calculate it from minus NR XA ln XA plus XB ln of XB. So that's norm. So like the general way to do it. So you can actually calculate N. I mean, you can use PV is equal to nRT. You have the information to do that. I think I misspoke earlier about not being able to calculate the number of moles, but you can calculate the number of moles, so you can go N is equal to, what's it, PV nRT, so it's equal to PV over RT. So I mean, you have enough information to do that. So you can figure that out. Or we also know that delta S mix is equal to minus the Gibbs energy of mixing divided by T. So I think that will just be a quicker route. So, go check yourself. So, so then we just plug this in. So what do we have up here? So that's 35107 minus 35107 and a bunch of numbers times 10 to the power 2 joule divided by the temperature, which was given as 25 degrees Celsius, so that's 298.15 Kelvin, of course. And then that then finally gives us a value of 1.17811176 and so forth, which can be rounded off to a value of 1.2 joule per Kelvin. Okay, so that's the entropy of mixing. Entropy, so Gibbs energy is negative, entropy is positive. Entropy is positive, why? Because of this order increase. Gibbs energy is negative because it's spontaneous. So both gives us an interpretation. Spontaneous, once the barrier is removed, the gases will mix spontaneously. Entropy increases because the disorder increases. The gases mixed, they're no longer separated. They're now disorderly mixed together. There's no dissociation between the two different gases anymore. Yeah, so some interpretation that you might get asked with the question, not just the calculation. They might get given the calculation and then ask for an interpretation. Right, so I think that's it. Just check that you do know how to do the mole fractions. The rest of it's quite straightforward. Yeah. There's some other examples, or the exercises also give are quite useful to go through, just to check that you have this, because these calculations are quite easy. They're not difficult, but there are like little things that I know generally are struggled with in terms of just mole fractions. For some reason, mole fractions are the most difficult thing for second years. But anyway, yeah,